So I want to look at a few of the major concepts in Chapter 7. Make sure we don't get confused on what all those things mean. And we started out talking about statistics, things that describe the sample, such as x bar, p hat, s, the lowercase n, and that was contrasted with parameters, which are things that describe the population, such as mu, sigma, p, which some books refer to as pi, or the capital N, the population size. From there, we could talk about taking a sample mean, which is the x bar, finding a bunch of samples, or we could also talk about finding the sample the sample proportion, a p hat, and the sample mean is a good estimate for the population mean, mu. So is the sample mean going to equal the population mean? Well, probably not. Okay, but what if we took a simple random sample? Would it work then? Well, still probably not, because of sampling variability. The sample mean is probably not going to be the right answer, but it ought to be pretty close to the right answer if we've taken some cautions along the way. Now, if I look at a sampling distribution, then I'm looking at the mean of all the sample means. And the mean of all the sample means, the mean of the sampling distribution, will equal the mean of the population, provided that I've taken a simple random sample. Otherwise, I end up with bias. So I could write that, for example, like this. The mean of all the sample means equals the mean of the population, or the mean of all the proportions in the sample, all the sample proportions equals the true proportion. And again, those are true if I've taken a simple random sample and therefore have no bias. We also discussed the central limit theorem, and the central limit theorem says as I take a larger sample size, then I get really three things. My sampling distribution will have the same center with a smaller spread and a more normal shape. Now, the center being the same, that's what I've done previously here in green. The smaller spread goes with the 10% rule, provided that I've sampled less than 10% of the population. I can use either of these two ideas to get the sampling standard deviation, which is also called the standard error. And then if I've taken a large enough sample size, if n is big enough, then I can think that it's pretty close to normal for me to go from there. Now, what is big enough for an n? Well, if it's a means problem, having an n of 40 will get the job done regardless of the original shape. If I know the original shape, something less than 40 may work. In fact, it'll likely work in a lot of cases, but 40 is a better safe than sorry kind of number. Now, with a proportion question, I need at least 10 successes and 10 failures in the group. I need NP to be bigger than 10, and n times 1 minus p bigger than 10. And if that's met, regardless of what shape I started with the original population distribution, then I end up with a sampling distribution that's approximately normal, close enough to normal for me to treat as normal. Now, we get a little bit confused sometimes with the difference between taking more samples and taking a larger sample size. And so I want to spend a moment talking about that. If I have a room full of minions and I send them all out to start taking samples of the height of young women, they can come back and report to me that after they measured 50 women, here's their X bar. And so I go up to the chalkboard and I start writing down these X bars and drawing a graph as my minions call the numbers out to me. After, 100 or so minions have called out their X bars that go with their individual samples of size 50, I have a nice little graph working on the board. Now that graph is not a sampling distribution, because a sampling distribution would be all possible samples of size 50, all the conceivable ways to arrange the women into groups of 50 and looking at them that way. That's the sampling distribution, the graph of all those different means. But I do have 100 now at this point, X bars up on the board, and I've got an idea of what that sampling distribution might look like. If another 100 minions give me their answers, that graph is not likely to change dramatically. And so you're like, wait a minute, coach, I thought you said if we did it with a larger sample size, we got a smaller spread. Yes, but remember in this case, the sample size is 50 for all of the minions. The difference lies with a different classroom. And in that different classroom, the minions are taking samples of 100 women at a time. Their graph is going to end up with a smaller spread and be more normal looking than the graph of the minions taking samples of size 50. That's the difference with the larger sample size.